fraction. Hello and welcome back to Calculus 3. This is section 13.7, change variables in multiple integrals, part 1. So the goal for this first part is to learn how to transform the region. Now, what does that mean? Well, before we dive into the whole thing, let's go and do the change of variables in one variable problems. Technically, what we are doing is U sub. So what is 13.7? 13.7 is U sub on steroids, which means U sub for 2D, 3D integrals, and so on. It can be done in any dimension. So, where do I begin? First, a review of what the U sub means from Calc 1. I have the integral from x1 to x2 of f of g of x times g prime of x dx. And then you go and you define the variable u as this g of x, and your du becomes the g prime of x dx. Now here comes the color. This part over here is your du, and this part over here is your u. We can also transform the limits. So u1 is g of x1, and u2 is g of x2. So now, if you are writing your calculus 1 u sub, you will write g of x1 to g of x2 of f of u du. Now, the top and the bottom limits are actually from u1 to u2. So the whole thing, well, I'll put it new integral. So the whole thing is actually integral from u1 to u2 of f of u du. This is Calc 1. This is Calc 1, and please observe what happened. We used to have the integral in terms of x. So what I had was x variable in the input, and then I was feeding in g of x and f of x, right? Eventually f of x on y. We transformed that integral completely into u f of u. Now some really scary functions become something very easy to work with when we do these things. Now this is called the change of variables, right? And you see that the variable x changes into variable u. Now our goal is to do the same in now multiple integration. Now what happens when you have more maybe I should, let me do one example over here. So integral 0 to 1 of x e to the x squared dx. So we go du u equals x squared, du equals 2x dx. So I need to add a half in front and have 2x e to the x squared dx. There we go. And now I still have 0 to 1 limits. So now what's happening? I'm going to, I don't like 0 to 1. Let's use 0 to 2. So now when I plug in 0 in original, I get 0, and u2 I get 4. So now it's 1/2 integral 0 to 4. 2x dx gives me du, and I have e to the u. You see, e to the x squared and e to the u are not the same functions. Not by a long shot are they the same functions. And then plus this times x and all of that kind of stuff. So we transformed everything. We transformed the x-axis into u-axis, and we transformed the function into a different function. So it's a complete change. And now we have e to the u from 0 to 4, which gives us 1/2 e to the 4 minus 1. And that will be the answer. What happens when we have multiple integrals? What happens when we get the 2D or 3D regions to transform? Well, it's much harder. It is much harder. What we need to consider now is first what we used to call u sub. Now we're going to call u sub, v sub, whatever you want to call it, right? It's going to be a transformation. What happened? You talking about these two? Yeah, I added those because I need the 2x for the 2x for the u sub. So now these two together are du, and the 1/2 I get to copy because it has nothing to combine with. Right? So when I take derivative over here, I get 2x. I don't have these 2 in original problem. So it is me who's adding these 2 out of nowhere, but I have to add 2 to make the substitution work. But because I'm adding that one, I have to counter it by this one. So now this is du. And this one I get to copy. Right? Make sense? You can achieve the same result if you go from here and you say, okay, what's x dx? Because that's what you have in original problem. X dx is du over 2. So you can put du over 2 and then kick the over 2 outside. So whatever way you like it. 2D. When I have 2D problem with a region, some function of xy dA, this can turn into dx dy problem or r dr d theta problem. It is very important to know that, yeah, I write it in blood, region is in limits of integration. We studied that before. You know that if you have integral of let's say 0 to 1 and 2 to 3, very like this, you know that your region is y is in between 0 and 1 and x is between 2 and 3. So you can graph this quickly in the space. Y is in between 0 and 1. and x is between 2 and 3. So this little square over here is your region R. And you read that from the limits. So our goal now is to transform that region into something else. Now, why would we be doing this? Well, the same reason like U sub in Calc 1. You can't integrate. And if you can't integrate, maybe U sub can help. Maybe by parts can help. Maybe trig substitution or partial fraction decomposition, right? Something else will work. Now, not to fear, there is not going to be a Calc 2 part 2 for Calc 3 integrals, right? You will see that the basic U sub is insane enough to do these calculations and things. So now, our job is to, looking at the transformation, is to transform the region that used to be a region, as you can see over here, in XY domain plane, and shift that into UV domain plane. So goal is to shift XY into UV. And when we achieve that, we are going to be able to do the integrals. So let's take a look at the transformation of the region. Now, I think they did 2 or 3 transformations in the section, so you can read and follow those. Well, I have only 7 minutes over here. I'll try to get it done in time. I just want to transform one region from homework, and then you can also read, you should read those that are done in the textbook, so that you have enough base to come in and do the heavy lifting on Wednesday, right? When we actually do these substitutions and transformations and things like that. All right, so let's transforming 2D regions. And if this book could move faster, that would be amazing. Every time I click, I have to wait 15 minutes for it to load the page. I just never to get to homework over here. Now I'm waiting like a minute per page to load. Finally. All right, so let's take a look at some transformations. I'm just going to pick up a transformation that it's given to us. So I'm working only on transformation. We'll do the full problems next time. So this is from problem 28. Region R is given to us as xy such that 0 less than x less than 2 and x less than y less than x plus 4. Well, use transformation x equals 2u and y equal 4v plus 2u. Well, first order of business is to draw to see what we have. So now I'm going to draw the XY plane. I'm going to now move the x-axis further down because it's x plus 4. One, two, three. Alright, so what do I have? I have a line over here which is x equals to y. That's a 45-degree line. Goes like this. So that's y equals x. When I'm done with that, I look at the second line over here, and that's y equals x plus 4. There we go. Y equals x plus 4. And now, looking at the bounds for x, it's from 0 to 2. So this is my region R. Not that bad, right? We can still do dx integral easily. Let's transform this region. The first order of business when you're transforming regions is to label each piece. You can label them in any order you want. You can say number 1, number 2, number 3, and number 4. So there are 4 lines that bound this region, right? 4 lines in the perimeter, and I'm going to label these 4 lines 1, 2, 3, 4. Now, number 1. Number 1 is just a horizontal line, x equals to 2, where y is stuck between 2 and 6. Do we see how this describes the first segment? So the line that we are dealing with is x equals to 2, and then y starts at y equals 2 and goes to y equals 6, and it stops. It's vertically up. Line number 2. Line number 2 is our good old line y equals x plus 4, and x is stuck between 0 and 2. Why am I doing this? Because this line is going to go forever to the left and forever to the right. So I fix y, and y is fixed through the equation, and I fix x, right? And x is between 0 and 2. Number 3. Well, we have x equals 0, and y stuck between which 2 values? 0 and 4. Very good. Finally, the 4th segment over here is y equal x, where x is stuck again between 0 and 2. Time to transform. So far, all we did is we drew the region, and we described by equations every single one of these pieces around. Now we just use the transformations to transform everything into u's and v's. So u's, x equals 2u, and y equals 4v plus 2u. I'll call this 1 star. So x equals 2. So I have 2u equals 2, from where u equals to 1. I also have that 2 is less than, and instead of y, I have less than equal to, So instead of y, I have 4v plus 2u. And then that's less than equal to 6. Now, I also know that u is equal to 1 from previous calculation. So actually, what I have here is 2 less than equal than 4v plus 2 less equal than 6. I can divide through by 2. 1 less than equal than 2v plus 1 less equal than 3. And now I need v alone, so subtract 1 everywhere. I get 0 less equal than 2v less equal than 2. And finally divide by 2 everywhere to get v alone. I have u equals to 1, and I have 0 less equal than v less equal than 1. I'm going to box those two. Region 2 star. I have y equals x plus 4. So y, that's 4v plus 2u, is equal to x, which is 2u, plus 4. 2u and 2u will drop. I have 4v equals to 4, v equals to 1. And I also have that x is between 0 and 2. So now, instead of x, I have to put 2u. And when I divide everywhere by 2, I get that u is between 0 and 1. Box those two. Region 3 star. X equals 0. Well, x equals 0 is 2u equals 0, so u equals 0. Nice. And 0 to 4. So 0 less than, this is 4v plus 2u, less than, I said 0 to 4? Yep. We know that u is equal to 0, so this dies. And from here we get 0 less equal than 4v less equal than 4, divide everywhere by 4. So we get that v is between 0 and 1. That's another set. And finally, fourth region. Fourth region is y equal x. So y equal x, so that's 4v plus 2u equals 2u. 4v equals 0, v equals 0. And we have the same x 0 to 2. Now x being 0 to 2, we know that from before. Gives us the same thing for u being between 0 and 1. And now that gives us the last set. If you carefully graph these onto the new coordinate system, what you have is this wonderful square 0, 1, 1, 1, 1 in a domain with u. So that transformation took a region R, which was a parallelogram, and transformed it into a square. Now we can take the parallelogram and make it into a polar coordinates. We can do all different tests. So you will see all different types of transformations when you try. So try transformations and then yes.
So are these transformations always given, or are they like bound each?
They are, well, they could be given, right? Generally, they're not given. You have to figure out what they are. Just the same like you pick your u sub. When you go into the problem, one that I have with e to the x squared, or you could have picked something else. It would work, right? So The reason why we give these transformations in class is because you really are not spending few days to figure out which transformation actually works. That's the reason. You are trying not just to fix it so the region transforms from something not friendly into something friendly, but you're also trying to pick something that will make the integral possible to solve. So there are those two levels, and clearly, right, the more dimensions you bring into this mess, the harder it becomes, because this is just the first step. Well, the first step is figure transformations, then transform the region, then find the Jacobian, and then replace everything, and then you start integrating. So these problems tend to be extremely, extremely long. But again, at least it's very systematic. So we've seen one of the steps of transforming the region. Next class, we are going to start the class with transforming one of the polar regions, and then move into the rest of the substitution part so that we have the complete picture. And then chapter 13 is over. See you all in 2 days, right?